What specific problem does the UI-R1 method aim to solve in the context of GUI action prediction tasks, and how does it address the limitations of supervised fine-tuning?
The UI-R1 method specifically aims to enhance the performance of GUI action prediction tasks, particularly in out-of-domain (OOD) scenarios, where existing models trained via supervised fine-tuning (SFT) struggle due to their reliance on large-scale, high-quality labeled datasets. UI-R1 addresses the limitations of SFT by employing rule-based reinforcement learning (RFT), which allows for effective model fine-tuning using only a limited number of training samples, 130 plus in this case, while utilizing predefined task-specific reward functions. This approach not only reduces the need for extensive human annotations, but also improves the model's adaptability and generalization capabilities across diverse GUI environments. The method incorporates a flexible reward mechanism that evaluates action type, action argument accuracy, and response format, ensuring that the model's predictions are both accurate and interpretable. Consequently, UI-R1 demonstrates significant performance improvements on OOD data, showcasing its efficiency and scalability compared to traditional SFT methods.
How does the proposed UI-R1 method work? Please illustrate the step-by-step methodology, including the generation of responses, the evaluation process, and how the reward mechanism is applied during training.
The proposed UI-R1 method operates through a structured reinforcement learning (RL) framework designed for GUI action prediction tasks. First, the model generates multiple potential responses trajectories for a given low-level instruction, which includes reasoning tokens and final answers. Each response is then evaluated using a tailored reward function that consists of three components: the action type reward, which checks if the predicted action type matches the ground truth; the action argument reward, which assesses the accuracy of predicted click coordinates against the ground truth bounding box; and the format reward, ensuring the model outputs reasoning and answers in a structured format. During training, these rewards are computed for each response, and the model is updated through policy optimization techniques like Group Relative Policy Optimization (GRPO), which normalizes the rewards to determine the relative quality of each response. This process allows the model to iteratively improve its reasoning capabilities and action predictions, while effectively utilizing a limited dataset of just over 130 high-quality training samples.
Can you provide a simple yet illustrative example of how the UI-R1 algorithm performs a low-level instruction, such as click the menu icon in the top left corner, walk through the steps of generating responses, evaluating rewards, and updating the model?
The UI-R1 algorithm processes the low-level instruction, click the menu icon in the top left corner, by first generating multiple potential responses, trajectories, that include reasoning tokens and the predicted action. Each response is then evaluated using a tailored reward function that consists of three components: the action type reward, the coordinate accuracy reward, and the format reward. For this specific instruction, the action type reward checks if the predicted action type, e.g., click, matches the ground truth, while the coordinate accuracy reward assesses whether the predicted click coordinates fall within the ground truth bounding box. After calculating these rewards, the model updates its policy using the Group Relative Policy Optimization (GRPO) algorithm, which normalizes the rewards to determine the relative quality of each response, allowing the model to improve its reasoning ability and action prediction for future instructions. This process ensures that the model learns effectively from limited data while enhancing its performance on GUI action prediction tasks.
What are the theoretical and practical benefits of the UI-R1 method compared to existing supervised fine-tuning approaches, especially in terms of efficiency and performance on out-of-domain data?
The UI-R1 method offers significant theoretical and practical benefits over existing supervised fine-tuning (SFT) approaches, particularly in efficiency and performance on out-of-domain OOD data. Theoretically, UI-R1 employs a rule-based reinforcement learning (RL) paradigm that utilizes predefined task-specific reward functions, allowing it to fine-tune models with only 130-plus high-quality training samples, in contrast to SFT's reliance on large-scale labeled datasets. Practically, UI-R1 demonstrates superior adaptability and generalization capabilities, achieving notable performance improvements on UD benchmarks, such as a 20% increase on ScreenSpot and a 6% increase on ScreenSpot Pro, while SFT's effectiveness diminishes significantly in UD scenarios due to its dependence on task-specific data. Additionally, UI-R1's approach to optimizing measurable objectives enhances model performance across diverse GUI-related tasks, showcasing its scalability and efficiency in resource-constrained environments. Overall, UI-R1 not only reduces training time and costs, but also maintains high accuracy and interpretability in its predictions, making it a compelling alternative to traditional SFT methods.
How was the effectiveness of the UI-R1 method validated? Discuss the experimental design, datasets used, and specific metrics employed to measure performance improvements.
The effectiveness of the UI-R1 method was validated through a series of experiments using two primary benchmarks, ScreenSpot and ScreenSpot Pro, which assess GUI grounding capabilities across various platforms. The experimental design involved training the Qwen2 5VL3B model on a carefully selected dataset of 136 high-quality mobile samples, chosen based on criteria of quality, difficulty, and diversity. Performance improvements were measured using specific metrics, including action type accuracy, which evaluates the match rate between predicted and ground truth action types, and grounding accuracy, which focuses on the accuracy of click action argument predictions. Results indicated that UI-R1 improved action type prediction accuracy by 15% and click element grounding accuracy by 20%, demonstrating significant gains even with limited training data. Additionally, UI-R1's performance was compared against other models, showcasing its superior capabilities in out-of-domain scenarios and its adaptability across diverse GUI-related tasks.
What limitations or drawbacks does the UI-R1 method have in terms of applicability or complexity, particularly in handling diverse GUI environments or scaling to larger datasets?
The UI-R1 method, while demonstrating significant improvements in GUI action prediction tasks, has limitations regarding its applicability and complexity in diverse GUI environments. One notable drawback is its reliance on a limited dataset of only 136 high-quality training samples, which, although effective for specific tasks, may hinder its performance in more complex or varied GUI scenarios that require broader training data. Additionally, the method's focus on low-level instructions may restrict its adaptability to high-level tasks, which could be prevalent in diverse applications. Furthermore, while the rule-based reinforcement learning approach offers scalability, the complexity of designing task-specific reward functions and ensuring they align with various GUI interactions can pose challenges, particularly as the action space expands. Lastly, the model's performance may diminish in out-of-domain UD scenarios, as indicated by the limitations of supervised fine-tuning (SFT) in adapting to unseen environments, suggesting that UI-R1 may also face similar challenges when scaling to larger datasets or more diverse applications.